Hello, this is Mr. McMurray, and we are just electrified to be talking to you about electricity. Very shocking subject, but we can deal with that. All right, first thing we talk about is electrical charge. Electrical charge is very simple. Electrical charges have two types of charges. You have positive charges and you have negative charges. Okay, and the two basic rules are if you have similar charges, like right here we have two positive charges, they will repel each other, try to go away from each other. If you have opposite charges, they will be attracted. Now, when they first invented charges, they called one positive and one negative, and they kind of picked them arbitrarily at first because they didn't really know what caused the charges. But basically, if they're two the same, they'll repel. If they are alike, they will. If they are, if they are the same, they'll repel. But if they are alike, they will be attracted. Hence the expression opposites attract. Try that in the dating scene at your own risk, but there you go. Okay, so that's basically the thing. If you have the same charges, they'll repel. If they have opposites, they will attract each other. Now, of course, that's fairly simple, so we can't leave it simple. That would just be wrong. As a scientist, it's our job to try to explain things better by making it more complicated. So why do things have charges and electrical charges? Well, basically, when we talk about the charge of an atom, we're talking about electrical charges, and electrical charges come from the atom. So let's look at the atom real quick. This right here would be an example of a helium atom. It's the second smallest atom. Hydrogen is smaller, and we'll talk about it later when we get to chemistry in the second semester. But for now, we're just going to settle into this one. But we'll settle for helium right now, okay? Helium is element number 2, and what this tells us is that in the center of helium you have two protons, okay, and the center of the atom is called the nucleus, okay, and you have protons, which are positive, and you have neutrons. Usually you have just as many, the same number, in this case 2 and 2, which is most common in helium, or you may have even more neutrons than you do protons, okay, and the neutrons are neutral. That's where they get their name, neutrons. So I would put them with a plus minus, which if you have a plus and a minus, they would cancel each other out. So that means that the electrons are neutral because they have they cancel each other out basically. Now, someone says, why do you need neutrons? They don't do much apparently. They just sit there. They're neutral. They have no charge. They do add mass to the atom. But what's their purpose? Well, we said what happens if you have two protons which are both positively charged. They are similar and they're going to repel each other. Well, it's very important the nucleus atom not repel itself, or all atoms would self-destruct, and that would not be a good thing since we're made out of atoms and everything around us is. So basically the neutrons possess a nuclear force that helps hold them, and the protons are attracted to each other, and it's a very tight force. This is why nuclear energy releases so much energy. If you can break that nuclear forces that hold these together, it would release enormous amounts of energy. It's a very, 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 very strong force. Okay, and so yeah, that's the nuclear force that holds the nucleus together. All right, that is not the force that we get from electricity. All right, you have electrons, which have a negative charge. Okay, they have an opposite charge, so you have positive and neutral charges in the middle. So basically, it has a positive nucleus. You have these negative charges around it, and just like the moon, these have a velocity, and they're trying to move. Inertia, Newton's law, first law, says they want to keep going the same direction they're going, but they also have this attraction toward the positive nucleus, and so instead of going straight ahead, they end up going somewhere in between, and you end up having this curved orbit around the nucleus. Okay, now this is not the same as gravity, because the force pulling it in is not gravity. The force is an electrical force. It's a completely different force, but it causes the same effect in that it gives you a circular or a orbit around there. So basically you have a positive charge, you have electrons. Now, if this were going to lose part of this atom, the center part has very, very strong, very, 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 very strong forces holding it together. And so it does not want to come apart. Also, it's in the middle of the atom. And as atoms get bigger, this is a very small one, they have layers and layers of electrons. And so really, the center part cannot change. So what happens is these outer electrons can be gained or lost. Okay? And if you were to lose a negative electron, let's just say this one bugged out on us, now we have two positive protons in the middle, but we only have one negative electron, and guess what? This atom would have a +1 charge because you have one more positive charge than you do negative. If it were possible, just for the record it's not, but just pretend it's possible, if it gained another electron, say it still had this one, and it gained this one, now it has a total of 3 electrons, then it would have a -1 charge because now it has one more electron than protons. So basically, when we say that things are positive and negative, electrically speaking, we're saying they're either gaining or losing electrons. And electrons are part of the building parts of atoms, and one electron can be traded with any other electron. They're identical. The protons and neutrons, the same thing. They're basically identical to each other and can be interchanged. But the protons and neutrons are in the center, so they're not ever going to leave the atom. Once they're part of that atom, they pretty much stay in that atom. But the electrons, since they circle around it, they can be taken off and lost and gained and added and so forth. So when things get charged, it's because they've either gained electrons or lost them. Now, if they have the same number, like we started off here with helium, then there we say they are neutral, and there is no charge for the atom. Okay, the atom has 2 positives in the middle, it has 2 negatives, and so it is a neutral atom. But if it was always neutral, then nothing would ever happen. Things would not stick together because you can't take 2 neutral atoms together, and that's why electrical charges are so important. Now, if it were to gain an electron, it would be called an anion, and it would have a negative charge. All right, think of A in ion. Ion just means an atom has a charge. An atom that has a charge is called an ion. If it's a negative ion, it's an anion. That should help. And if it's positive, it's called a cation. I don't know how to help you with that one, but I positively hate cats, so cations are negative. Whatever helps you remember, there you go. All right, so if it gains electrons, becomes more negative, it's an anion. If it loses electrons, it becomes more positive, then it is a cation. All right. Now, notice when we say if it loses this electron doesn't disappear. It just goes somewhere else to another atom and hangs out on that other atom. Okay. If it gains electrons, it doesn't just poof out of thin air. It comes from another atom. And so you cannot gain or lose electrons. You can just move them around. So this is known as conservation of charge. In other words, the number of protons, electrons, and charges stays the same, but they can change from one atom to another and move around, especially the electrons at any rate, can move around, but they do not get destroyed in order they get created. There's only a certain number of them. All right, now, there is a law that describes how much force electricity is, because electricity is once again a force, okay? And the law for that is called Coulomb's law, after a man, I believe, named Charles Coulomb, who established this relationship. Okay, Coulomb's law. Okay, and Coulomb's law should look a little bit familiar. Let's spell law correctly. There we go. All right, Coulomb's law looks a lot like another law we already talked about, and that is gravity. We said the force of gravity, G instead of E, was equal to G times the mass of one object times the mass of the second object divided by the distance squared. Well, electricity has a very similar formula. Instead of the constant G, we have a constant called K. We have, instead of masses, we have charges, which are called Q1 and Q2. And these are just the charge of the 2 particles, or 2 objects that we're talking about here. Okay? And this is how we measure how much force these 2 objects attract each other with. All right? So the force between them depends on the amount of charge. The more charge the 2 objects have, then the greater the force of attraction. And it depends on the distance. Once again, the inverse square law kicks in. The farther the 2 particles get away, it exponentially decreases the amount of force that they exert on each other. So they need to be fairly close, which in an atom, which is what we're talking about, they are fairly close. So the distance is very small. This number is very small. And this number is relatively large. Okay? Now, K, if you remember, G on gravity was 6 point something times 10 to the -9th or something to that effect, or 11th, something to that effect. Okay, K is equal to 9.0 times 10 to the 9th. This is 9 billion, basically. Okay, this is a big number. Now, the number over here, you don't really need to worry about, just to know this would all cancel out, and it would give force in newtons. That's really all this unit has. We're not worried about that. But notice this number. This is what's important. 9 billion. This is a very big number. Gravity was 10 to the negative 11, 0.000000, 10 zeros, and then a 6. So basically, electricity as a force is a billion, double billion, plus a little more, times stronger than gravity. Much, much stronger. If you had small particles like the protons and the electrons, gravity, the mass of these objects are so small that the force of gravity between them would be nothing. Okay, it would not exist. Even you and your desk, which are fairly massive objects compared to an atom made of billions and billions of atoms apiece, and you still don't feel the force of gravity between you. Okay, so electricity is very, very strong. It's way stronger. Okay, just for example, we measure the charge in coulombs. If two particles had 1 coulomb and 1 coulomb, all right, coulomb. Each one had a charge of 1 coulomb, all right, and they were 1 meter apart, like a yardstick, basically. Okay, and they were 1 meter apart. The force between them would be equal to basically 9 billion newtons, which is the weight of a battleship. Okay, big, humongous war battleship. That the force of gravity pulling down that would be equal to the force of these two particles with 1 coulomb apiece, 1 meter apart from each other. Enormous amount of forces. Now, granted, the force is not usually a whole column between these two, much smaller than that. Okay, and their distance is also smaller. But the forces are smaller. But compared to gravity, the point is this is a whole different kind of force. Electricity is a much, much stronger force than gravity. Gravity is considered a very weak force. Now, compared to the electrical force, the nuclear force that holds the protons and the neutrons together is even a stronger force, but we're not going to get to that right now. But let's just know, main thing I want you to know, that between gravity and electricity is much stronger. Now, the other difference with electricity is electricity can, and we kind of talked about this a minute ago, can attract objects or it can repel objects, whereas gravity can only attract. The force of gravity can only attract two objects. There is no repelling involved. But since we have positive and negative forces in electricity, they can repel and attract. And so that's makes it more, I guess, useful, you could say, in nature, because you can put things together as well as take them apart. How does this charge thing work in real life? Let's look at an example. Say I have a plastic rod. I rub it with a silk rag here. And basically, as I rub them, some of the electrons on the silk rag will transfer themselves, come off basically, and stick to the rod. So that gives the rod a positive charge, a negative charge, because it has more negative electrons than it normally did. They were neutral before I started rubbing it. Now it has some extra electrons, and so it has a negative charge. Okay, that means that the silk rag over here would have what kind of a charge? Well, it lost the electrons, which are negative. So if you lose negatives, that makes you more positive. So it would have a positive charge. So this would have a positive charge over here, and this would have a negative charge. And so since there's the same number of charges, and we gave some over here, one becomes negative, the other becomes positive, and the number of charges is still the same. Now, in that case, the charges are transferred from one object to another. There is another type of charge, which we call charge polarization. Polar meaning having two poles, one positive, one negative, or sometimes it's called charge induction, or inducing a charge. All right. If I have something that has, let's just say, a positive charge, say I take this silk and I bring it close to an atom. Well, normally I'd have a positive nucleus and all the electrons would be attracted to it, and it would be evenly dispersed, and so you would have a neutral charge. But if I bring a positively charged object over here, so now we have a positive object over here, it's going to attract the electrons over here, and you're going to have an overload of electrons on this side, making it kind of negative and attracted to the positive object. And the positive charges are going to be repelled because like charges repel, and they're going to attract over here to the other side. And so in this atom, this side is more negative, this side is more positive. So that the net charge of this atom is still the same. You still have the same number of electrons as you had before. You didn't gain or lose. And so it's the same.